Thank you very much for the introduction. Also, thank you very much for the organizers. It was a really nice, or is still really nice workshop. And also thank you for the opportunity to tell the audience about our nice user laboratories that we have at the European XFEL. And for anyone who might not know where we are located in really close to the very beautiful city of Hamburg. It's always worth a visit, especially in spring and summer. And not only the city is really pretty, also our labs are really, really nice. Our accelerator starts at DESY, which is located in the federal state of Hamburg. And there the underground electron tunnels start and then are divided into underground X-ray tunnels in Schleswig-Holstein in Schenefeld. Then the tunnel is 3.2 kilometers long. And amongst others, experiments that can be done here is a serial femtosecond crystallography experiment, and the XFEL is 10 to the power of 9 times brighter than the synchrotrons, and this enables us to get signal even from really small protein crystals with really short X-ray pulse durations, and enabling us to get these molecular movies we heard about so much already. And this also helps us with radiation damage and to do the experiments at room temperature. What is special about the European XFEL is this burst of X-ray pulses that come in the sponge structure. Also this we heard before, right? But so we have here these bunches of X-ray pulses, and then we have this break in between. This has the disadvantage, let me say, that we lose the sample in the meantime, because we use liquid jets, really fast liquid jets. They have to be super fast, so every X-ray pulse or the jet is being hit by every pulse, so it has to be quite fast, or like really fast. And second, we lose in between the sample that never sees an X-ray. Because of this, this we also saw, so I will quickly go through it. At the XFELs we can probe really short time scales that can't be probed by synchrotrons yet. And we normally do this by mixing and pump probe experiments, which is maybe more for this audience. And to do these pump probe experiments, we need super small microcrystals, maybe also nanocrystals, and this is helpful because the smaller the crystals, the shorter the diffusion time is, and also the penetration times for the pump laser. And for this we need billions of crystals. So as you can imagine, it's tedious to prepare the sample. And also the sample requirements are quite unique if you use a liquid jet in comparison to maybe fixed targets or other less sample consuming delivery methods. So the crystal densities you need is 10 to the power of 10 per milliliter crystal to get like a reasonable hit rate. Then the crystal should be homogeneous. This is especially important for mixing and also for pump probe with the laser. And therefore the crystallization protocol should be really, really established and reliable, and we recommend using batch. So you have the possibility to create this large amounts of crystal slurry that we need. Most of the time the jets run at like 10 to 20 microliters per minute, so this really you need like milliliters, tens of milliliters and grams of protein for a successful experiment with different time points. The viscosity of the precipitant also extremely important. This can lead to nozzle clogging, which also leads to your precious sample loss and also time loss during the beam time. And last but not least, the diffraction of the protein crystal should be really good, so you can see these really small differences in your electron density at the short time scales. And for us in our user labs, we kind of have like these four parts that make like the sample really good and can lead to a successful sample delivery, which is the quality, the density, the viscosity, and the homogeneity. Normally we just use the stereo microscope to assess the density and the homogeneity of your sample, We use the TEM also for checking the quality, and we use the jetting test station for the viscosity and also the density of the sample. And all of this we assess before your beam time, before the sample actually sees the beam, because this can save you valuable beam time and also the valuable sample. Where do we do it? Is here in the biolabs. The biolabs were created with the XBI user consortium, which consists of Arizona State University, EMBL, Ministry of Education, Science, Research and Sport of the Slovak Republic, the University Hospital and the University of Hamburg, Uppsala Universität and the University of Oulu. And the aim here was to create a lab environment where you could do everything that is needed for sample preparation for a successful experiment. Our spacious labs, it's like 500 square meter. They are located above the experimental hall and also have the sample elevator here, so you can directly put your prepared sample there and it goes directly down to the SPB SFX hutch. I think this happened before, right? Okay, so also we have a lot of specialized rooms, and also for light-sensitive proteins, importantly, we have several sample environments that can be operated in either red, green or blue light. This is a crystallization room, our cold room, our dark room, which is just like a miniaturized lab, has everything you need, and also our glove box room, where we have a really big glove room that can then also be used for sample preparation. This I just briefly show you just that you get an expression what kind of equipment we have, and we have a lot, and you can do everything here from cloning to expression in different strains. For purification of your protein, characterize the protein, crystallize your protein, characterize then your sample, and also for the sample injection. Here's our new addition that we have since recently. It's a Raman spectrometer that is coupled to a confocal fluorescence microscope. It's also enabling different kinds of characterization. And I want to give an example. So we have a TEM, the expert is Robin, and we bought it kind of to characterize our sample, but it kind of evolved in something that we do regularly. And what we do, for example, if you have different crystal batches and you're not sure which one you want to inject first, then we can check the different crystal batches and check if they actually diffract. And also what you can do with the TEM is to distinguish between amorphous precipitate or actual nanocrystals that are so small that you can't really see it in any stereo microscope. And what we observed is that you can see for like really small crystals, you can see the crystal lattice, and you can also get some electron diffraction, which indicates that it will also diffract downstairs at the beam. We also had a case where we had like something, we were unsure, is it crystalline or not? So there was like a kind of a lattice visible here, but we didn't see any electron diffraction, and also this crystal then did not diffract downstairs. And this is also something Robin showed yesterday, which I really like to show. This is like for the I don't know, most optimized case, optimal case where you have like such a nice crystal where the lattice is so highly ordered that you can even put in your pi mole model and it fits. Yes, and so we kind of do this regularly now to see if the samples, or which of the samples gives the best electron diffraction, and then hopefully the best results downstairs. Then we also have a huge part of our group is working on the sample delivery, therefore like also on the development of different liquid jets, and we will test beforehand the conditions of the jetting. This is then, for example, also done in here, not only liquid jet, but also in high viscosity extruders. And we have like a setup that resembles the setup downstairs, so we can kind of mimic as good as possible the situation downstairs at the instrument. And we also have an advanced testing station where you can actually like measure the speed of of the jet and also do some fluorescence imaging. In that case, we test the mixer we developed if the mixing is efficient while using a GFP variant that can be quenched. And you also can check the stability of your jet over longer times. And also, in that sense, we also have different 3D printed nozzles. We decided to print all our nozzles with a 3D printer to make it more reliable and also easily adjustable. So we have a selection of standard nozzles such as the GDVN, like the most standard one that is regularly used, and also the double flow focusing nozzle and high viscosity extruders. But also if you, for example, have a special requirement for your experiment, you can also talk to us and we can make adjustment to the designs. And if you are a group that produces your own nozzles, you can also come to us and test them before. Or you can send us the design and we can print it out and test it without you coming. And we also provide flat sheets for spectroscopy applications. All the designs that we have are published and they are also uploaded to GitHub, and everyone who wants can use them and optimize them, print them, and so on. In the last minutes, I want to show you the opportunity to write a proposal for our PCS beam time. It's a sample and protein crystal screening beam time. We have a call starting later this year. The next call for the proposal, sorry. And what is changing in comparison to how we did it so far is this will be more on a rolling basis. So it will not be like this fixed slot we have once a run, so it will maybe open up other possibilities. And what is really nice here, we encourage people that didn't work with any X-FELS so far. They might lack the experience, they don't know how to really prepare the sample and so on and so forth. And in this framework, we can really support you. We can help you with preparing your sample. Maybe if you have problems making microcrystals, we can help you. We can characterize the sample. We will also, during the beam time, help you with or do the injection for you. We provide the nozzles, and we also help you with the data analysis. And what you will get is 3 hours of beam time, or 3 hours of beam, actually. This is enough for a static structure, for example. And with this data, you then have like higher chances to write a full proposal. And our contact person is Katharina Dörner. You can write her an email if you have questions. And also the other thing I want to present is we have here an internship program. These internships are designed to develop beam time projects, and in this framework we offer 4 to 8 week internships. If applicable, you can participate in X-FEL experiments. You will get time and resources to develop your own projects. You have the chance to contact and network with the scientists at the European X-FEL, and if you're from Europe, we will cover the travel and the accommodation costs during the internship. If you're interested, you should be a PhD student or a postdoc, and you should have a project that would benefit from using X-FELs. Be independent and open to learn new things, and all you need to do is write a brief description of the research project you have, a short CV, and a support letter from your supervisor. And also, if you're a group leader or a PI, if you know anyone who might be interested, please spread it. It's also not exclusively for crystallographers, so it's also like for other people that might benefit from the use of a free electron laser. Yeah, and with that, I want to thank my group and you for your attention.